Thank you so much for the introduction and the invitation. It's a great pleasure to speak here. Um, so, so let me start with some notations. So we take F to be a number field, A is the ring of adults, and we fix a non-trivial additive character psi on A, which is trivial on F. So we have a pair of quadratic spaces over F, Vn and V of n plus 2l plus 1 of dimension n and dimension n plus 2l plus 1. So here Vn is embedded in V of n plus 2l plus 1, and L is a non-negative integer, n is a positive integer. So we have the embedding of their associated spatial orthogonal groups. So SOVN is embedded in SOV of n plus 2l plus 1. Their GSpin groups are the GL1 extensions of the associated spatial orthogonal groups. And we have an embedding of the GSpin groups also. And we have this diagram where so there is a projection map. There's a projection from the GSpin to SO, and the kernel of the projection is in the connected component of the center and is isomorphic to GL1. Moreover, we have this commutative diagram where the vertical arrows are inclusions. So in this talk, to simplify notation, we will write GSpin n to be GSpin of Vn. So inside inside this GSpin V of n plus 12 plus 1, we consider the standard parabolic subgroup Q sub L, which stabilizes a complete flag of isotropic subspaces determined by Vn perb. So the Lavie subgroup L sub L is isomorphic to GL1 to the L times GSpin n plus 1. And then we can realize this GSpin Vn in a concrete way. So we can define a character psi sub L comma A. This is a character of n sub L associated to psi and some element A in F cross. Then this Lavie L sub L acts on the character, and the stabilizer is G-spin of n. So now we take phi to be an automorphic form on G-spin n plus 2l plus 1, and phi prime to be a Cas form on G-spin n, so that if we take their product, restrict to the connected component of the center, we get 1. So phi z times phi prime of z equals 1 for all z in the connected component of the center of the G-spin groups. Now, the Bessel period for the pair phi and phi prime with respect to the character size of L comma A, this is defined in this integral over here, where we first take the Bessel Fourier coefficient of phi. This means that we take this Fourier coefficient with respect to n sub L and the character size of L comma A. We take this Fourier coefficient first and pair it with the Cas form phi prime, and then integrate it over G-spin NA, quotient by G-spin NF, and the kernel of the projection A. So, so this is the Bessel period. We first take the Bessel Fourier coefficient and then pair it with a Cas form phi prime. Because of the assumption 1, here, this integrand in the Bessel period formula here, this is invariant under the kernel of the projection, so that we can quotient this out. So these formulas were defined. And then since phi prime is a cusp form, the integral defining this Bessa period is absolutely convergent. So here we just need to take a phi to be any automorphic form, but phi prime we need to take a cusp form. And here there is a subgroup here, which is the semi-direct product of n sub L with GSpin n, and this subgroup is called a Bessel subgroup of GSpin n plus 2L plus 1. So this is the definition of the Bessel period, and this is a global object. There is a local analog of the global Bessel period, which is called the local Bessel model. And in Pierce's work, I proved the uniqueness of the local Bessel models. So we take nu to be n in place of f, either Archimedean or non-Archimedean. And we take pi nu, sigma nu to be irreducible admissible representations of GSpin n plus 2L plus 1 f nu and GSpin n f nu. And in the Archimedean case, we assume that these are of Kazman-Wallach type. Then we have that the dimension of this Hom space is at most 1. So previously, in the spherical case, in other words, when L is equal to 0, so that the quadratic spaces associated to these two G-spin groups differ by one dimension. In this case, the above result was proved by Amory Takeda in 2023 in the non-Archimedean case, and by Amory Kim Matty in 2025 in the Archimedean case. So our proof here is to reduce the above problem to the spherical case. In other words, given a element in this Hom space, we can construct certain element in a Hom space that corresponds to the spherical case, and then so that we can use that bound in the spherical case to get the result here. Okay, so this is the uniqueness of the local Bessa models. Back to the global situation. So the main goal of this talk is about the global Gan-Gross-Prasad conjecture, which was proposed by Gan and Gross and Prasad in 2012 in this paper, in this very influential paper. So they formulated a conjecture for classical groups and metaplatic groups that links Bessel period to central L value. And based on the formulation for special orthogonal groups, we can formulate the analogous conjecture for G-spin groups by taking care of the center. In other words, when we define the Bessel period, we quotient out the kernel of the connected component of the center to make this integral well convergent. So here is the global Gan-Gross-Prasad conjecture for G-spin groups. So let pi sigma be irreducible tempered cuspidal representations of G-spin n plus 2L plus 1 and G-spin n respectively, such that omega pi times omega sigma equals 1. So here omega pi and omega sigma are the central characters of pi and sigma restricted to the connected component of the center. And so this condition will make the integrand invariant under the kernel of the projection. We assume that they occur with multiplicity 1 in the discrete spectrum. Then the following are equivalent. First, the Bessel period for phi pi, phi sigma is non-zero for some cusp form phi pi, cusp form phi sigma. in the space of pi and sigma. And then the second statement is that the central value for the L function for pi times sigma is non-zero. So this is the global Gan-Gross-Prasad conjecture for GSpin groups. And so there has been a lot of progress on the classical group side. I want to highlight that in 2020, Dihua Jiang and Lei Zhang made a breakthrough on this conjecture, and they proved the direction 1 to 2 in full generality for special orthogonal groups and unity groups using the Rankin-Selberg method together with endoscopic classification for these groups. And they also proved the direction 2 to 1 under some hypotheses. And here is the abstract of their paper. On the GSpin side, the spatial case GSpin 5, GSpin 2 was considered by Prasad and Taglubikhash in 2011. So in view of the isomorphism that GSpin 5 is isomorphic to GSP4. And in 2020, Melissa Emery formulated a Aichino-Akita type global GGP conjecture for GSpin n plus 1, GSpin n. So in the co-dimension 1 case, and she proved it completely for n equals 2, 3, and in certain case for n equals 4. And her approach relies on the accidental isomorphism between low-rank GSpin groups and classical groups so that one can reduce the problem to the low-end cases on the classical groups. So, so global GGP for GSpin groups is low end in some very low rank spatial cases. And our main result is that we prove one direction of the global GGP conjecture for generic representations of GSpin groups. And the direction is 1 to 2. So take pi and sigma to be reducible generic cuspidal automorphic representations of GSpin n plus 2L plus 1 and GSpin n, respectively, such that omega pi times omega sigma equals 1. If the Bessel period for pi and sigma is non-zero, then the L function for pi and sigma is holomorphic and non-zero at 1 over 2. So this is our main result. And this result works for arbitrary n and L. So this is the most general situation. And the first ingredient of my proof is a new family of Rankin-Selberg integrals for the L functions of GSpin times GL. And our proof of the main result is an application of the Rankin-Selberg integral in a similar way as in Jiang and Zhang's work. So, so now let's talk about the first ingredient of the proof, which is a new Rankin-Selberg integral for GSpin groups. So we take pi and sigma to be cuspidal representations of GSpin n plus 2L plus 1 and GSpin n, so that omega pi times omega sigma equals 1. So in the construction of the Rankin-Selberg integral, we do not assume that pi sigma are generic. This works for any cuspidal representations, and the generic condition will come into play later when we prove the global GGP. So, and the tau is a generic isobaric automorphic representation of GLK of A. So here we assume K is greater than L. And the goal here is to construct an integral representation for the L function for pi times tau. So if we're given pi and tau, and then their sizes are determined determined, then we can always find some sigma, which is on the smaller GSpin group. So if n plus 2 l plus 1 and k are determined, we can find some n so that k is greater than l. So sigma here is auxiliary. It will play a role in the construction. So that's our goal. Now, for in terms of the Rankin-Selberg integral, we want to construct an integral representation for pi times for the L function for pi times tau. So curiously, we have GSpin n inside GSpin n plus 2l plus 1. When we talk about the global GGP. So now we introduced tau, which is a representation of GLK, and k is greater than L. So we can actually embed further GSpin n plus 12 plus 1 inside GSpin n plus 2k. So we have these three GSpin groups, which I refer them as small GSpin, middle GSpin, and large GSpin. So we denote L prime to be k minus L minus 1. Then GSpin n plus 2k, the large GSpin, is going to be the GSpin of the size of the middle plus 2L prime plus 1. So L measures the difference in size between the small and middle GSpin group. L prime measures the difference in the size of the middle and the large GSpin groups. Okay, so we have three GSpin groups. And pi is on the middle and the sigma is on the small GSpin groups. So now inside the large GSpin, we take pk, which is a standard parabolic subgroup, whose Levy factor is isomorphic to GLK times GSpin n. And we can form an induced representation of the large GSpin group, inducing from tau tensor sigma, where we twist tau by determining absolute value to s minus 1 over 2. So there's a complex parameter s going on here. And then we define an Eisenstein series associated to a section F in the induced representation. So this Eisenstein series is defined in the usual way. So the Eisenstein series depends on tau and sigma, and there's a complex parameter S. So this is an Eisenstein series on the large GSpin group. So now in the large GSpin group, we can also form a Bessel subgroup H prime, which is an L prime semi-direct product with the middle GSpin, where an L prime is a unipotent subgroup. So here I'm writing this unipotent as an element in the associated spatial orthogonal group. But the unipotent subgroups of GSpin are isomorphic to unipotent subgroups of the corresponding spatial orthogonal groups. So I'm actually writing this in terms of the image under the projection map inside SO. So here we have Z here. Z, this is upper triangular unipotent of size L prime times L prime. And there's Y and X over here. Y prime depends on Y. So that's a unipotent. And similarly, the middle GSpin n plus 2L plus 1 is the stabilizer of a character on this unipotent. Okay, so now we take phi pi to be a non-zero cusp form. Then we define the global zeta integral as the Bessa period for the Eisenstein theories and the cusp form for the pair large G-spin, middle G-spin. So we take the Bessa Fourier coefficient of the Eisenstein series and then pair it with the cusp form on the middle G-spin. So this is the definition of the global zeta integral. Um, and this integral converges absolutely and uniformly in vertical strips in the complex plane away from the possible poles of the Eisenstein theories, and hence it defines a meromorphic function on the complex plane with possible poles at the locations where the Eisenstein series has poles. So this is the global integral we want to study, and we want to establish a formula with between this integral and the L function. So to establish an integral representation, our first step is to unfold the global integral into an Euler product of local integrals. So we start with unfolding the Bessel coefficient of the Eisenstein series. So we're looking at this term here. We can start by writing down plug in the definition for the Eisenstein series. So that's going to be a sum over G-spin m plus 2k quotient by pk of f. So now what we do is we let PL prime to be the standard parabolic of the large G-spin, whose levy is isomorphic to GL L prime times G-spin m plus 2 L plus 2. And then let PL prime act on this cosine space. And then we arrive at the second line over here. So this is a sum over representatives of the double cosine space. So epsilon is a representative of this double cosine space. And then we take an integral of n L prime. And then this inner sum is over PL prime F, quotient by the stabilizer of the action of the representative epsilon. So we get this expression here. Then the next step is to look at the inner summation, and we use H prime to act on this quotient space. So recall that H prime is the Bessel subgroup of the large G-spin m plus 2k. So we can further rewrite the Bessel-Fourier coefficient of the Eisenstein series into a sum of epsilon in this double coset space, and then a sum of eta, which is a representative of the second double coset, and then integral and then summation of H prime F quotient by the stabilizer of eta, and then we have this term over here. So now we can plug in this formula to the global zeta integral so that we arrive at the following expression, and we interchange the summation with the integration to get the following expression over here. Okay, so we're gonna use the following two facts to eliminate all the terms in the summation except one. So there is a summation over epsilon over eta here, but eventually only one term survives in the summation. And the first fact is that if S is a unipotent subgroup, and if psi sub S is a non-trivial character on SA, which is trivial on SF, then the this integral of psi s is 0. Um, and then the second fact is that if U is a unipotent radical of a proper maximal parabolic subgroup of the middle G-spin, then if we take the constant term of the cos form phi pi over U, then we get 0. And this is due to the causality of the cos form. So eventually, we are gonna get one term, um, and the global zeta integral unfolds to the following expression. Um, so the integral here is over the adelic points of G-spin n plus 2L plus 1 quotient by H, which is the Bessel subgroup of the middle G-spin. And this B here, this is the Bessel period for pi sigma prime, where sigma prime is obtained from sigma by a conjugation. In particular, if sigma prime is on a odd G-spin group, then sigma prime is just sigma by, itself. And then we have pi g act on the cos form phi pi. So that's the first entry of the Bessel period. And then the second entry of the Bessel period is the following. Uh, there's a J here. So J, this denotes taking a Fourier coefficient with respect to the adelic points of U0, of some unipotent U0. So J is decomposable because here it's integrating over adelic points. There's no quotient by the rational points here. And then R denotes the right translation action. And then epsilon eta, those are Y group elements coming from double coset decompositions. Um, and then F sub W tau sigma S, this belongs to the following induced representation. This is similar to the previous one, to the original one, but here we take the Whittaker model of tau with respect to a generic character instead of tau. So, by the uniqueness of the Bessel models for G-spin groups, we can decompose the global integral as an Euler product of local integrals. And the local integral at a place nu looks like the following. So B nu is a local Bessel functional for pi nu tensor sigma nu prime. And the V pi nu is a vector in the space of pi nu. And then everything else is just, so here everything is just taking the local component after the unfolding of the global integral. And F here is a section of the local induced representation. So that is the local zeta integral. And the next step is to compute the local integral at a finite unramified place. So we take the following data for the local unramified computation. We take nu to be a finite place such that everything is unramified. And we take unramified vectors in the space of pi nu and sigma nu. We normalize the local Bessel functionals in the way such that when we plug in the unramified vectors, we get 1. And the section is also unramified and normalized in a way such that if we plug in the identity element in GSpin and an element in GLK F nu, we get the Whittaker function evaluated at A times the unramified vector of sigma nu, where this Whittaker function is also normalized unramified such that it's value at the identity matrix is equal to 1. So when we choose these data for the unramified computation, we can compute this integral explicitly to get the following expression. So we get in the numerator the L function for pi nu times tau nu. In the denominator, we get the L function for sigma nu times tau nu twisted by the central character of pi nu. And also the exterior square or the twisted exterior square or symmetric square L function for tau nu at 2s. So here, rho here is either the exterior square or symmetric square, depending on whether n is even or odd. And we need to twist that by the restriction of the central character of pi nu into the connected component of the center. So that's the local unramified computation. So once we have the local unramified computation, we have the following integral representation. So we assume pi sigma prime has a non-zero Bessel period. If pi sigma prime does not have a non-zero Bessel period, then the global integral is equal to 0. So now we take pi sigma, we assume pi sigma prime has a non-zero Bessel period. Then there's a choice of data so that this global zeta integral is equal to this partial L function, this expression times z sub s, where the capital S is a finite set of places, including the Archimedean ones and also the non-Archimedean ones where the representations are ramified. So it's a finite set of places. And then Z sub S, this is the finite product of local integrals over places in capital S. And again, rho is either exterior square or symmetric square, depending on whether n is even or odd. So this is a new Rankin-Selberg integral for GSpin times GL group. So the L function here that in terms of integral representation, the L function we obtain is pi times tau through this integral representation. And again, in terms of the Rankin-Selberg integral, we do not assume pi and sigma are generic. And when pi and sigma have trivial central characters, the above result recovers the construction of Dihua Jiang and Lei Zhang in 2014 for quasi-split spatial orthogonal groups. And when pi is globally generic, when pi is globally generic, tau is cuspidal, and pk, which is used in the construction of the Eisenstein series, is the zygoparabolic subgroup of the large GSpin. Then such construction appears in a recent work of Asghari, Cogdell, and Shahidi in 2024 using an Eisenstein series associated to the zygoparabolic subgroup. So our construction is a generalization of their work. And also in the spatial case, when n equals k equals 2, L equals 1, our integral representation recovers the integral representation of Furusawa in 1993 for GSpin 4 times GL2 L function, in view of the isomorphism that GSpin 5 is isomorphic to GSP4. So this is the first ingredient of the proof of the global GGP for generic representations of GSpin groups. The second ingredient is the description of the image of the functorial transfer for generic representations of GSpin groups due to Asghari and Shahidi. So so we take Gn to be a quasi-split GSpin to n plus 1 or GSpin to n. and let pi be an irreducible generic cuspidal representations of Gn, then pi has a unique functorial transfer to an automorphic representation of GL2n, denoted as capital pi. This capital pi signifies that it is isomorphic to its countergradient, twisted by restriction of the central character of pi. And the representation capital pi is an isobaric sum of the following form, where each piece, capital P, pi I, is an irreducible unitary cuspidal representation of GLNI, such that there is a L function condition for each of the piece capital pi I. The completed L function for either the exterior square, twisted exterior square, or twisted symmetric square L function has a pole at s equals 1 in the odd case or in the even case, respectively. Moreover, each capital pi I is isomorphic to its countergradient tensor with omega pi for each I, and each piece is different from each piece pi I is different from pi j if I is not equal to j. Conversely, any automorphic representation capital pi that satisfies the above conditions is a functorial transfer of some generic cuspidal representation of the GSpin groups. So this result gives a complete description about the image of the functorial transfer for generic representations. So now let me give you a sketch of the proof of one direction of the global GGP for generic representations. So now we assume pi sigma are generic. Remember, in the construction of the Rankin-Selberg integrals, we do not need to assume pi sigma are generic. But when we prove the GGP, we need to take this assumption. And we also assume that the Beza period for pi sigma is non-zero. And we want to show that the central L value is non-zero. The first step is the Rankin-Selberg integral. This is the first ingredient in the proof. Notice that the global zeta integral, if we take sigma in the Eisenstein series, it will unfold to the Beza period of pi sigma prime. So to get the Beza period, we just take sigma prime in the Eisenstein series. So we have this global integral. It is factorizable, and we get an integral representation. This is step 1. Step 2, we take tau to be an irreducible unitary generic isobaric representation of GLK associated to distinct tau 1 tau r, such that tau I countergradient is isomorphic to tau I tensor omega sigma inverse for each I. We can prove the following statements. So the L function of sigma prime times tau twisted by omega sigma inverse is holomorphic at 1/2. And the Eisenstein series, so this is Eisenstein series that's used in the global zeta integral, is inducing from tau twisted by determined absolute value to the s minus 1/2 tensor sigma prime. So this Eisenstein series can possibly have a pole at s equals 1 of order and most r. So this r is coming from the number of pieces in tau. So the Eisenstein series can have a pole at s equals 1 of order and most r. And we can give a description of when that happens. So it has a pole at s equals 1 over order r if and only if the L function of tau, the twisted exterior square or symmetric square L function of tau I has a pole at s equals 1 for each I, and the L function of sigma prime times tau twisted by omega sigma inverse is non-zero at s equals 1 over 2. So this is step 2. Next step, we're gonna use our integral representation. We normalize the local zeta integral, say nu, by dividing by this script L, where this script L is the expression we get when we do the unramified computation. So in other words, the normalized local zeta integral is equal to 1 at a finite unramified place. So we normalize our local zeta integral in this way. So now we take capital pi to be the functorial transfer of small pi. So we know pi is generic, so the functorial transfer exists. And we know the properties of capital pi. There is a description about the image of the functorial transfer by Asghari and Shahidi. And now we take tau to be capital pi tensor omega pi inverse. So this is a representation of GLK. So when we take this particular tau we can show that the completed script L, this is taken the product of the local script L, which is this expression. We can show that this expression has a pole at s equals 1 over r, and this is coming from the numerator, this term of here, the L function of pi times tau. And we can also show that the local normalized integral over places in capital S is holomorphic at s equals 1 for any choice of smooth smooth sections. And this step is proved by using the identity that the global zeta integral can be written as the completed script L times the normalized local integrals over places in capital S, and also using step 2, part 2. Okay, so that's step 3. Step 4, we can prove that if we are given a point s equals s0 in the complex plane, if the local Bessa functional is non-zero at all the places in capital S, then there's a choice of data so that the finite product of the local zeta integrals over capital S is non-zero at this given point S0. So this step is very technical, and the main technical challenge is to construct a section that satisfies the property that gives a non-zero value to the local integral. So this is step 4, and then recall that we assumed that the global Bessa period is non-zero. So as a priori, we only know that this global Bessa period is non-zero for some choice of phi pi, phi sigma for some cos forms in the space of pi and sigma. But we can actually prove more. We can actually prove that there exists a choice of data so that both of these two quantities are simultaneously non-zero. the second one is the Bessel period. The first one is that the local zeta integrals. So with the given choice of data, phi pi, phi sigma, the local zeta integrals over places in capital S. This is step 5. And then step 6. So with the above choice of data, we can prove that the global integral has a pole at s equals 1 over order r. So with that information, then we can deduce that. So the pole comes from the poles of the Eisenstein series. We can deduce that the Eisenstein series has a pole at s equals 1 over order r. This follows from again this identity where the global zeta integral is equal to the completed script L times the local normalized integrals over places in capital S, as well as the fact that this completed script L has a pole at s equals 1 over order r in step 3, and the normalized local integrals over places in capital S at s equals 1 is non-zero from step 5. So that's step 6. So now, once we have that, then we can combine step 2 and step 6 to say that, so step 2, part 3, says that the Eisenstein series has a pole if and only if there's a L function condition on tau I, and also this L function, L of sigma prime times tau tensor omega sigma inverse is non-zero at s equals 1 over 2. But this L function is the same as because of the relation of capital pi and tau, this is equal to the L function for sigma prime times capital pi, but capital pi is the functorial transfer of small pi, so this is the same L function of sigma prime times small pi, but sigma is just a conjugation, so this L function is the same as sigma times pi, and that concludes the proof of one direction of the global GGB conjecture for generic representations. Okay, so we prove that in 7 steps. As another application of the Rankine-Selberg integral, we obtain a reciprocal long-vanishing result of Bessel periods. So this is a result that relays the long vanishing of Bessel periods for 2 pairs of GSpin groups. So recall that we have the small and middle and the large GSpin groups. And so here we have actually 2 pairs of the GSpin groups, the large one and the middle one. So that forms a pair of GSpin groups, and we can talk about the Bessel models for this pair. There's another pair, which is the middle GSpin and the small GSpin, and we can talk about the Bessel model for that pair as well. So when the Eisenstein series has a pole at s equals 1 over order r, we denote by this script E the residue of the Eisenstein series at s equals 1. And here is a reciprocal long vanishing result of Bessel periods. We take pi sigma to be reducible generic Caspidal representations of GSpin n plus 2L plus 1A and GSpin n of A respectively, such that omega pi of omega sigma equals 1. We take capital pi to be the functorial transfer of small pi, and we take tau to be capital pi tensor omega pi inverse, and we'll assume that the residue of the Eisenstein theories is non-zero. Then the following are equivalent. First, the Bessel period for the residue of Eisenstein theories and pi is non-zero for some choice of data. If and only if the Bessel period for pi sigma is non-zero for some choice of data. So here is the direction 1 to 2. This is an immediate consequence of the Rankin-Selberg integral. But 2 to 3 direction, so if we start with the Bessel period for pi sigma non-zero, and we want to prove the Bessel period for the residue of the Eisenstein series and pi is non-zero. So the proof of that is along the same line as the proof of the one direction of the GGP outlined above. So it's a byproduct of the above proof by using step 1 to step 6 in the previous slides. And I will stop it here. And thank you so much.
Okay. Thank you very much for the nice talk. I guess we can give some digital applause. Yeah. So, are there any question for Pan? So maybe I have just a general question about the like framework of the GGP. Is it expected that there is a direct relation between, like, actually an equality between the Bessel period and the L value?
That's
Because
a
the proof, like for this case, is quite indirect. It seems like you have to go through all these steps and then yeah.
yes. So that's a good question. So in the case of GSpin n plus one GSpin n, so in other words, when L is equal to 0, then Melissa Emery formulated a precise formula between the Bessel period and the central L value. So that's the Achino-Akita type GGP conjectures. That gives the explicit formula. And she proved it for n equals 2, 3, and in certain case for n equals 4. In general, it is expected there is also such a formula similar to the special orthogonal group case.
Okay, so in the special orthogonal group case, there is a conjecture, or it's
Yeah,
already
it's
proved?
a Achino-Akita type conjecture.
Um, but then this increments go from n to n plus one. Uh,
So uh, in the special orthogonal group case, there is this conjecture that for special orthogonal groups that works for arbitrary Bessel models, there has been some progress on it. In the GSpin case, there is just right now is just this codimension 1 case conjecture
I
for
see.
GSpin. Yeah. In the general case, there is we don't have a explicit conjecture yet for GSpin in the general for a general Bessel model.
Do you think it's hard to formulate such a conjecture? And if you have such a conjecture, do you get the other direction of this GGP?
Um, I think that's a very good question. I have not looked into the Achino-Akita type conjecture yet. But once we have this result of the Achino-Akita type result for global GDP, then yes, then we can prove to the equivalence of this the long variation of the Bessel period between the long and the long variation of the central L value.
I see. And how close are this Ichino-Ikeda type conjecture for the G-spin, the codimension one G-spin, and then the codimension one special orthogonal group?
It's very similar.
Uh,
Yeah, it's very similar. So one just needs to take care of the center of
okay.
GSpin. It's very similar. Yes.
Do you think one can get from the one to the other?
Yes, I think it's doable from the Aichino-Aikido type conjecture for special orthogonal groups to GSpin. I think that's doable.
Uh-huh. Okay, I see. Yeah, thanks a lot.
Thank you for the questions.
Uh, are there other questions? Uh, I should stop the recording. Uh,